This is a continuation of the EE5508 optical processes in semiconductors. In the last session, we discussed example 9. Today, we'll discuss the mechanism of photoluminescence. Now, previously we have discussed absorption, basically the incoming photon energy to excite the electron near the top of the valence band to near the bottom of conduction band. And this is the absorption experiment to measure the band gap energy. In this session, we discuss the photoluminescence after the electron they have been excited from the valence band to the conduction band, and they recombine to give out light. So the sample is mounted in the cryostat. With the cryostat, it can vary the temperature. An incoming laser which provide the photon energy to excite the semiconductor sample. And after the electron excite from the valence band to the conduction band and recombine to give out light. So this light that is emitted will be collected, by collection lens and focused onto the entrance slit of the spectrometer. So the spectrometer, as we have discussed previously in the absorption experiment, sometimes we call that the monochromator, consists of mirrors and the diffraction grating. So the entrance slit, where the light entered and then get reflected by the mirror, the diffraction grating is mounted on the turret where it can be rotated and light, can be diffracted into the exit slit. So by the diffraction grating, you can select the wavelength of the light. And then from the exit slit, the signal is detected by the detector and then connect to the computer. And you also can connect basically the spectrometer to the computer, and you plot the intensity of the emission wavelength, the intensity of the light as a function of the emission wavelength. For optical transition in photoluminescence, let us discuss the shape of the band-to-band photoluminescence spectra. Let us assume a direct bandgap semiconductors and the joint density of state that we have discussed in session 2.3. The density of state is involved because it involves the valence band and the conduction band, where the electron and hole recombine. Now, Fe and Fh represent the Fermi-Dirac distribution for the electron and hole in the conduction band and valence band. So for low photo excitation density, basically the incoming photon energy, the intensity is not too high. So the photo excitation density is low. The Fermi-Dirac distribution of the electron and hole can be approximated by a Boltzmann distribution. And the luminescence intensity or the photoluminescence intensity is a function of the photon energy and can be written in this form. The joint density of state, which involves the valence band and conduction band, and how the electron is being distributed after excited to the conduction band, leaving the hole behind, how the whole carrier is being distributed in the valence band, which is governed by the Fermi-Dirac distribution. And the proportionality constant here, m squared, is called the matrix element that involves the probability of the optical transition. And this involves quantum mechanics to obtain the matrix element. So we will basically take the matrix element, approximately to be 1 over tau r, where tau r is the radiative minority lifetime, carrier lifetime. So this metric element is basically the electric field, okay, coming from the photon energy, okay, interacting with the electron. So the Fermi-Dirac distribution, again, the product of Fe and Fh will be of this form. And remember, from the conservation of energy, H bar equals to Eg, H bar squared, K squared over 2 mr star. This term is actually the electron energy plus the whole energy. So therefore, electron energy plus the whole energy will be equals to H bar omega minus Eg, which is this term. So the photoluminescence intensity can be rewrite as the density of state multiplied by H bar minus Eg goes at square root 2, which is this part is the density of state, the joint density of state, times the Boltzmann distribution, okay, due to the product of the distribution of the carrier in the conduction band and the valence band, and multiplied by a proportionality constant 1 over tau r, which is some numerical number. Okay, this is the theoretical plot of the photoluminescence intensity as a function of the photon energy. So based on this equation in 2.6.13, okay, which is written down here again, is basically the product of the density of state, okay, which is proportional to H bar minus Eg goes at square root, times the product, the blue curve, which is the exponential decay due to the Boltzmann distribution of the carrier. So after multiplying these two factors, you will get a spectrum like this. And this is the photoluminescence spectrum. Now there's this term called full width at half maximum. Basically at the maximum intensity, which is at the peak of the spectrum, and you divide, okay, into two parts, or at the middle part, which is 50%, you measure this width, okay. So this is known as the full width at half maximum. Sometimes we call this the line width. Okay, you take the peak intensity, and then at the 50% value, this is the full width at half maximum. So you can see that the recombination of the electron and hole, they give out the emission intensity or the luminescence intensity. This will look like the PL spectra. Okay. The peak itself is not exactly at the band gap, but is plus kT over 2. So it's temperature dependence. This is an experimental result of the band-to-band photoluminescence spectra. Basically, the electron and the hole recombine for N-type indium antimonide measured at 4.2 Kelvin. Okay, the solid circle, okay, are calculated result based on this equation. Okay, the solid curve is basically the measured result. So the solid curve is an experimental curve, and it fitted to this equation, which is the solid data point. So it fitted quite well, okay, from this part onwards, okay, based on the PL, okay, theoretical analysis. However, you'll see some deviation at the low photon energy. Okay, this we have discussed before. This is due to the band tiling effect. which occur not only in the absorption, of course, in the emission as well. Now, the band gap depends on the temperature. So the band gap of the semiconductor depends on the temperature. Okay, this is the band diagram, or the energy as a function of the interatomic spacing. So you have encountered this in Prof. Wu's course. Basically, in the isolated atom, your electrons are tightly bound and have discrete sharp energy. So when two identical atoms are brought closer, the outermost orbit of this atom overlap and interact. So the wave function of the electron of different atoms to begin overlap considerably. So the energy level corresponding to this wave function will start to split. Okay, and with more atoms are brought together, more levels are formed. So for a solid of n number of atoms, each energy level of the atom will split into n level. And then they will brought closer together, they form continuous band. That's how the conduction band and valence band are formed. Okay, n is the energy is a function of the interatomic spacing. So the band gap of semiconductor, okay, tends to decrease as temperature is increased. Now this can be understood qualitatively because if we increase the temperature, you are increasing the thermal energy. So it causes the amplitude of the atom vibration to increase. And you basically will cause the interatomic spacing to increase. So this is basically known as the linear expansion coefficient of the material. So as the atomic interspacing decreases, you expect the potential seen by the electron in the material reduces the size of the energy gap. So imagine down here, okay, is the original interatomic distance. And then as you increase the temperature due to thermal expansion, you expect basically your energy to shift to here. So this value, okay, this vertical distance will be smaller than this distance as your interatomic spacing increases, because this defines the gap of the semiconductors. So essentially, you can think of it this way. You need thermal energy to increase the atomic vibration. And therefore, your atomic spacing actually increases. So once this is a plot of interatomic spacing as related to energy, as your interatomic spacing, okay, increases, this gap, okay, you move towards the right, and therefore your band gap actually decreases. Another way to look at it is, if you decrease the temperature, you contract the crystal lattice. So you are actually strengthening the interatomic bond. And therefore, you moving in this direction, the energy gap actually increases. Okay, so this is true for most of the majority of the semiconductor. So this is a plot of the band gap energy as a function of temperature. You can see that as you increase the temperature, okay, the band gap energy decreases. As you decrease the temperature, the band gap decreases. So for example, gallium arsenide was quoted as 1.43 eV. Okay, that was assuming the value is at the room temperature. At low temperature, you expect the band gap to be higher. At a higher temperature, the band gap will be lower. Similarly for silicon, even for direct band gap like gallium phosphide, and even for carbon. Now, the band gap as a function of temperature can be related by this equation. This is known as a Varshni's relation, where alpha and beta are the fitting parameter. E naught is the band gap at temperature equals 0. So with this data point, the solid circle, you can fit the equation, okay, or you can fit the data point by using the Varnish equation by adjusting the alpha and beta, okay, parameters as adjusting parameters. However, there's no physical meaning to this value of alpha and beta. They can relate to the physical property of the semiconductors. Another equation, okay, that has been developed for temperature dependence of the band gap is of this form. Okay. Again, EG0 is basically the band gap at temperature equals 0. H bar omega involve the phonon energy. So this basically demonstrates the relative coupling constant, okay, the strength of the electron and phonon interaction on the semiconductor band gap energy. So the S itself is basically the coupling constant. So this table shows the temperature range of the silicon, the temperature, the band gap at temperature equals 0, okay, the relative strength of the electron and phonon interaction. H bar omega is the phonon energy involved. Okay, remember that the band gap is a function of temperature. As you increases the temperature, okay, the electron will interact with the lattice, and your lattice thermal energy will increases. Therefore, the electron and phonon will have to interact, and that will affect the band gap energy. So the band gap energy, okay, is related to the electron-phonon interaction. Next, another type of transition is known as the free to bound transition. Let us look at one example. Let us consider photoluminescent experiment on a p-type semiconductor sample, basically containing Na acceptor. Okay, the number of acceptor or the concentration of the acceptor is Na. So at low photo excitation, the incoming photon energy is low, okay, and therefore the density of free electron that you created in the conduction band, because you are exciting the electron in the conduction band, is much smaller than the acceptor density. So basically, there's a lot of acceptor, okay, down here, and you come in with a photon energy, okay, you excite enough electron, but much less than the acceptor concentration. So it goes up, and then the electron will recombine, okay, with the acceptor. So this is called free to bound transition. Free because free carrier for the electron conduction band, and hole in this case, which is a charge that is bound to the impurity. So therefore, this is not a free to bound transition. So the emission after the electron and hole recombine at the acceptor, you give up the photon energy. And that will give you the band gap minus the ionization energy of the acceptor, which means that this is the band gap, and then minus off the EA, which is the acceptor ionization energy, or the shadow acceptor binding energy. Next is the figure that shows the electroluminescence of a p-type gallium arsenide measured at 4.2 Kelvin for different dopant concentration. Okay, it ranges from 3.7 times 10 to the power 17 per cm cube to 1.9 times 10 to the power 18 per cm cube. So, starting off with 3.7 times 10 to the power 17 per cm cube, and then you increase the concentration to 1.9 times 10 to the power 18, and then 1.3 times 10 to the power 19, and 1.25 times 10 to the power 20. You can see that the emission spectrum actually shifted to a lower photon energy, or the peak, which is closely related to the band gap, actually shifted to a lower photon energy. And this, we have discussed, is due to the band gap renormalization. So for p-type and gallium arsenide, let's say you do it with zinc, okay, you expect several of the interesting changes. You can see that the carrier distribution function become degenerate, because if we increase the carrier concentration, the Fermi level goes into the valence band. So mode transition occur. And furthermore, the high energy side, okay, previously we said that it can be resemble the Boltzmann distribution. Which is this case. So this, the Fermi-Dirac distribution is approximated by a Boltzmann distribution. However, a high doping concentration this is no longer true. For example, 10 to the 20, this resembles more like a Fermi-Dirac distribution. So you cannot use this equation, to fit the photoluminescence spectrum. For this part, which is a Boltzmann distribution, you have to use the full Fermi-Dirac distribution function. Okay, so this is the full Fermi-Dirac distribution function. You can only approximate to a Boltzmann distribution at low concentration on non-degenerate semiconductors. So the peak in the emission spectra rate shift, that means shift to a longer wavelength or smaller photon energy with increasing doping is due to the band gap narrowing. So it shifts to a lower photon energy. Now, the radiative recombination rate for the free to bound transition, since you do it with p-type, again, you go back to equation 2.6.6, where we have the recombination lifetime depend on the carrier concentration. And you can approximate this and 1 over time to be depends on the acceptor concentration, which is P naught. And you get, let's say, for 10 to the power 18 of Na, which is the acceptor concentration, you get about a lifetime of 1.4 nanosecond due to the recombination of the electron with the bound hole or with the acceptor. Next, another type of transition is the donor-acceptor pair transition. Let's say you have semiconductor that contain both donor and acceptor. So such an acceptor are said to be compensated. So some of the electron from the donor will be captured by the acceptor. So as a result, the compensated sample contain both ionized. So this is the conduction band, this is the valence band. this is the donor level, this is the acceptor level. So the donor level is filled with electron, acceptor is filled with hole. D naught means neutral donor, A naught means neutral acceptor. If you come in with a photon energy, at thermal equilibrium, okay, without any photon excitation, okay, there's a probability the electron can be captured by the hole, okay, without any incoming photon energy. So the electron can recombine with the hole, and that gives rise to D plus and A minus, ionized donor and acceptor. So any sample you put on the shell, okay, there's a probability that the electron and the hole can recombine, but the probability is low, okay, especially at room temperature. In any case, now you come in with the incoming photon energy. You can excite the electron from the valence band to the conduction band, and this electron can be recaptured by the donor. Again, for the other one, the electron can be recaptured by the hole. So you go back to D0 and A0, and the electron and hole can recombine to give out light, which is at the energy of Eg minus Ea minus Ed, but you need to plus a Coulomb attraction term. So basically, it's the band gap Eg minus Ed, the donor binding energy, Ea, binding energy of the acceptor. However, the electron and hole, okay, have a Coulomb attraction, okay, because electron is negatively charged and the hole is positively charged. So you have to add another term, okay, due to Coulomb attraction. And the R here is the separation, okay, between the donor and the acceptor, which is the Coulomb energy, E squared over 4 pi epsilon R. Again, epsilon is a dielectric constant, okay, is related to the relative dielectric constant of the semiconductor. So in terms of the whole reaction, initially it's neutral state, okay, you come in with a photon energy plus the ionized state of the donor and the ionized state of the acceptor. So electron, the donor and the hole, okay, can be separated far apart. So we call this the remote pair, or they can be very close together, almost a lattice constant apart. Okay, for example, about 5 Armstrong apart. So these are close pair. So by optical excitation, electron and hole can be created in the conduction band and valence band, and this carrier can then be trapped, okay, at the ionized donor level and acceptor level, and the electron and hole can recombine to give out light. However, electron and hole, okay, you have to add another term called the Coulomb attraction term. Okay, this is due to the separation between the ionized nodal and the acceptor. Now, donor-acceptor pair, one of the good example that has been best studied is in the gallium phosphide. And there's two ways to basically introduce the donor acceptor in the gallium phosphide. So gallium phosphide is a host atom. So gallium, we call it the gallium sublattice. Phosphorus is the another sublattice. So there are type 1 and type 2. Type 1 is where the donor and the acceptor are located on the same sublattice. So basically, you can have phosphorus, okay, being replaced by sulfur and silicon. Okay, because sulfur is group 6, phosphorus is group 5. So a group 6 replaced with a group 5, you have additional electron, that is donor. So sulfur is a donor. And then if you use silicon to replace phosphorus, silicon is group 4, phosphorus is group 5, you short 1 electron. And so silicon is an acceptor. Okay, so the sulfur and silicon occupy the phosphorus sublattice. And this is a type 1 donor acceptor pair transition or DA pair transition. Another type is type 2, okay, where both donor and acceptor occupy different sublattice. So for example, sulfur occupies the phosphorus sublattice, the zinc occupies the gallium sublattice. So sulfur group 6 replace group 5, that is a donor. Zinc itself is group 2, you place a group 3 element, which is gallium, and that become the acceptor. So you have type 1 and type 2 donor acceptor pair transition. So this shows the gallium phosphide where you have silicon sulfur or even silicon telluride. So these are the type 1 DA pair transition. So all the sharp peaks here are basically due to the donor acceptor pair transition. Okay, and each peak is due to the separation distance between the donor, ionized donor, and the ionized acceptor. Okay, you don't worry too much about this number. Basically, this is due to the theoretical fitting. Okay, they give rise to some of the shell number of the pair. So again, all these sharp peaks are due to the donor acceptor pair transition, and each pair is separated by a certain distance between the donor acceptor. Example, how to calculate the donor acceptor pair transition. So let's say you have a photon energy. You want to calculate what is the transition energy from the shallow donor to the shallow acceptor in germanium. And if the donor acceptor impurity is separated by 40 Armstrong, and given the donor acceptor energy at the ground state is 9.3 MeV and 10 MeV respectively, basically the binding energy of the donor and the acceptor are 9.3 and 10 MeV respectively. Band gap of germanium is 0.66. Relative dielectric constant is epsilon r, which is equals to 16.2. So the photon emitted in the donor acceptor pair transition is basically Eg minus Ea minus Ed plus the Coulomb attraction term. So Ea and Ed is given to you. Okay. Epsilon is epsilon r times epsilon naught, where epsilon naught is the dye permittivity in free space, which is 8.85 times 10 to the power minus 12. And then the R itself is 40 Armstrong, or 40 times 10 to the power minus 10 meter, or 10 to the power 4 times 10 to the power minus 9. So you can calculate basically the Coulomb attraction term is about 22 MeV. So you take the band gap minus the acceptor minus the binding energy plus the Coulomb attraction, that gives you 0.6627 EV. Now, this is the last type of the transition. We call it the optical band trap transition. Now, basically, you have a band gap of semiconductor like gallium phosphide, which is an indirect band gap semiconductor. In fact, gallium phosphide semiconductor, which is an indirect band gap, was first used for LED. Even though it's an indirect band gap semiconductor, the result is as follows. The gallium phosphide indirect band gap is about 2.26 eV. And then you introduce an impurity level, and it can become a very efficient light emitter. So for example, you introduce nitrogen. Now, this nitrogen will replace the phosphorus and introduce an energy level below the conduction band of about separation about 50 MeV. Now, nitrogen is not a shallow impurity in gallium phosphide because nitrogen is group 5 and phosphorus is also group 5. So if gallium phosphide is doped with nitrogen, of course we say it's doped, but not the kind of shallow doping. So some of the phosphorus atom will be replaced with nitrogen. So the nitrogen has the same number of valence electron as phosphorus. So it does not contribute to the electronic conduction, just like the shallow impurity. But this nitrogen actually acts as an isoelectronic trap. Isoelectronic trap, basically it can bind the charge carrier. If there's a large difference in electronegativity between the center and the atom is substitute for. So the electronegativity for the nitrogen, and the phosphorus are very different. So there's a large difference in electronegativity. And so this nitrogen, when in gallium phosphide, it will introduce level below the conduction band, and it can bind electron or can bind carrier. So in this case, nitrogen in gallium phosphide has a larger electronegativity than phosphorus. So it will induce a binding of the electron. So electron that is tightly bound to the isoelectronic center actually can be governed by the uncertainty principle. Why is it so? Let us look at this diagram. This is the energy spatial diagram, which is in real space. This is the energy EK diagram, which is in the momentum space. If you draw two straight lines, this is the band gap energy of the gallium phosphide, which is 2.26 eV. From the spatial diagram, you cannot see that this is a direct or indirect band gap. You introduce a level 50 MeV below the conduction band. Now, the electron is very localized here. So it's bound by the trap. Now, if you convert to reciprocal space, then the wave function will spread out in the K space. So if we plot the energy as a function of K, this is the indirect band gap. And then below the conduction band, you will have an energy level due to the nitrogen doping in gallium phosphide. So if it's very localized in real space, we expect the electron wave function to be delocalized in the reciprocal space. So the electron, based on uncertainty principle, there's a probability that you can find the electron above the top of valence band, and you can make such a direct recombination to give out photon energy. Otherwise, If the electron is down here, this will involve a change in the in K, or the change in momentum. So the efficiency of this recombination is very small. So the probability K of finding electron here is due to the uncertainty principle, because based on uncertainty principle, delta X, delta P will be much, much greater than H bar over 2. So delta X, K is very small, so it's very localized in real space. And in reciprocal space, K involve the K, so the change in K is very large. So if there's a possibility, okay, you can find the electron at the top of valence band, and this electron can recombine with the hole, okay, near the top of the valence band. So this is the optical transition, okay, occur while a deep level state. Again, I just want to recap oxygen and zinc, okay, donor and acceptor in gallium phosphide. And there is also a possibility that the electron in the donor and the hole can recombine, okay, with the acceptor also to give out light. Another way is by introducing nitrogen in gallium phosphide, and that also can give out the light emission. Next topic is the acetone. So there are two types of acetone called the Werner mott acetone and the Freckle acetone. Acetone is a very complex concept. Basically, it involves a free hole in the valence band and a free electron in the conduction band. And because they have opposite charge, positive and negative, they experience a Coulomb attraction. So the electron can orbit about the hole as if they are like a hydrogen-like atom. It's very different from the donor-acceptor pair transition. The donor-acceptor pair basically is involved the donor and acceptor, and it depends on the crystal lattice, the crystal structure, and the distance between the donor and the acceptor. In this case, for acetone, okay, you have to solve through Schrödinger equation, and the acetone basically is a concept of the Coulomb attraction of a free electron in the conduction band and a free hole in the valence band. Now, for Werner mott acetone, basically the electron and hole, okay, they have Coulomb attraction, but they are weakly bound. The electron and hole separation is large, so it's cover many lattice spacing. So these are lattice spacing between the atoms. So you can see the electron and hole, okay, the distance between them is large. However, you take the electron and hole, okay, as one particle because there's still a weakly bound through a Coulomb attraction. Another type of acetone is called the Freckle acetone, where the separation between the electron and hole is of a lattice spacing apart. So the Coulomb attraction is very strong. So these are tightly bound acetone. And Werner mott acetone usually observed in semiconductors, while the Freckle acetone are found in insulator and molecular crystal. Okay, so Werner mott acetone are basically weakly bound electron and hole, okay, attracted to each other by Coulomb attraction. So sometimes we call this the free acetone. And the attraction is weak because the separation between electron and hole is large. They cover many lattice spacing. So in this figure, okay, we see that the electron and hole are bound together so they can move as a single quasi-particle. And they can move freely throughout the crystal in the uniform dielectric material, which is in this case the semiconductors. Again, we can model the free acetone as the hydrogenic system. For hydrogen, you have a light electron and a heavy proton. For semiconductor, the acetone basically have comparable mass. So for example, in gallium arsenide, electron effective mass about 0.06 m naught. The hole effective mass about 0.45. And compared to hydrogen atom, okay, the free electron mass is 9.11 times 10 to the power minus 13, while the proton mass is very large. It's 10 to the minus 27 kilogram. But your gallium arsenide electron effective mass and hole mass, okay, is a factor of the free electron mass. So compared to, even though we use a hydrogenic model because of the negative and positive charge, for gallium arsenide semiconductors, okay, we expect the stability of the exciton is lower compared to the hydrogen atom. So the binding of the hydrogen atom will be much stronger than the acetone. However, we will use the hydrogen model, okay, to describe the free acetone because of the negative and the positive charge. So for fractal acetone, okay, which occur in molecular crystal, we just briefly mentioned that it has a much smaller radius because the electron and hole separation is about lattice constant apart, and it can be found in alkaline halide crystal in molecular crystal. Now, the acetone is stable only if the attractive potential is strong enough to prevent the acetone from breaking up owing to the collision with the phonon. So if you treat the acetone, okay, as one particle, due to the Coulomb attraction between the electron and hole, so this particle will move inside the crystal, and the binding energy of the crystal must be at least, okay, less than equals to kT. The reason is because this acetone will collide with the phonon or with the lattice, and the electron and hole will break apart. So the binding energy, okay, must be less than kT, okay, or must be greater or equals to kT. Okay, if the kT is greater than binding energy, then the electron and hole will dissociate. Okay, they will break into free electron and free hole, no longer form an acetone. So kT is the thermal energy. So for example, in gallium arsenide, at room temperature, the kT itself is about 25.9 MeV. The binding energy of the acetone is about 5 MeV. So at room temperature, okay, you do not expect to see acetone, okay, because the thermal energy will break up the electron and hole into a free electron and free hole, okay? So there's no more of acetone that's been formed. So the binding energy of the acetone gallium arsenide is about 5 MeV. Gallium nitride is 28 MeV. So at room temperature, your thermal energy kT is about 25.9 MeV. If your gallium nitride is 28 MeV, which means that your binding energy of the acetone is greater than thermal energy. So you can see acetone effect in gallium nitride. So the thermal energy is not sufficient to break the acetone into a free electron and free hole. Zinc oxide, the same thing, 60 MeV. So you expect to see acetone effect at room temperature. For factor acetone, the binding energy is even larger. Okay, this is 0.1 to 1 eV. So if you use KT at room temperature of 300 Kelvin, it's about 25.9 MeV. Most of the volume acetone or the free acetone in semiconductor, okay, cannot be easily observed. But however, if you lower the temperature, then your KT will be lower. Then you will expect to see acetone at low temperature. Now, in order to understand the acetone concept, we need to use Schrödinger equation to derive its kinetic energy. So Coulomb attraction between the conduction electron and the valence band hole will form the electron hole pair, which is called the exciton. So the exciton, just the electron and hole, have wave function. Now, because the exciton is the formation of the bound electron hole pair, free electron in the conduction band, and free hole in the valence band, it will consist of an envelope function. And this envelope function basically is the function of the wave function of the exciton. Okay, will have to partly, okay, due to the contribution of the block function of the electron and hole, because the exciton is due to the formation of the free electron and free hole. So if you look at the Schrödinger equation, the kinetic energy of the electron, the kinetic energy of the hole, and then you need to add the Coulomb attraction term. And this is the wave function. And this is the energy of the acetone itself. So you have to solve this Schrödinger equation. So we break the Schrödinger equation, okay, into two parts, similar to the hydrogen atom. One is the center of mass coordinate, and one is the relative coordinate. If you look at the next picture, okay, if we have two mass, one, let's say the electron mass, the other one is a whole mass. So there's a center of mass motion. So if you take this as origin, so this is the center of mass coordinate. The relative coordinate will be x1 in respect to the origin minus x2. That is the relative coordinate between the electron and hole. So the center of mass coordinate will be written in this form, and the total mass will be me plus mh star. The relative coordinate will be just Re minus Rh, and it will be associated with a reduced mass. So similarly, the wave function itself can break up into the center of mass coordinate and the reduced mass coordinate. So that is the wave function. So the energy of the acetone will have two parts. One is the center of mass, and the other one is the relative coordinate energy. So if you solve the Schrödinger equation, you can break up into a center of mass motion and the relative motion. So this is the center of mass related to the energy, the center of mass motion. And the small r, okay, they involve the Coulomb attraction, will relate to the relative motion. So it's easy to solve the center of mass motion. So this is basically the second order differentiation of a wave function. The wave function can be found to be EI dot r, where Kc is a center of mass wave vector. The kinetic energy will be just h bar squared Kc over 2m. The big M is the total mass, the electron hole. For the relative motion, okay, This is known as the Wiener equation, and this can be solved, okay, very similarly to the hydrogen atom. And I will just quote the result for this equation. Basically, it's mathematically equivalent to a hydrogen Schrodinger equation. So the energy itself, okay, in this case, if you model after the hydrogen atom, the Mr star will be the reduced mass of the electron effective mass and hole effective mass, and it will involve, okay, the Rydberg energy, which is 13.6 eV, which is the binding energy of the hydrogen atom. Epsilon R is the relative dielectric constant of the semiconductor, and N is the integer. So this part, okay, I will call it the epsilon B. So the kinetic energy of the exciton due to the relative motion will be minus epsilon B times 1 over n squared. If n equals to 1, okay, then we'll just put ER equals to minus epsilon B. This will be the exciton binding energy, which bind the electron and hole at n equals to 1. RH itself, again, is the Rydberg energy, is the binding energy of the hydrogen atom. Now, hydrogen atom, the lowest orbit, we call that the Bohr radius. The radius of the exciton, of course, exciton also have its orbit. So the radius of the exciton, okay, is expressed in this form, and is expressed in terms of AH, where AH is the Bohr radius of the hydrogen atom. So M0 over Mr star times epsilon R times AH, I call that the Bohr radius of the exciton. And N is again an integer. Now AH is the lowest orbit of the hydrogen atom, and it has been calculated to be 0.0529 nanometer. So I express the Bohr radius of the exciton in terms of the Bohr radius of the hydrogen atom. So for n equals to 1, the free exciton is the largest binding energy and the smaller Bohr radius. So if you go back to the slide 55 on the Mach transition, I also talk about the Bohr radius. So for the donor Bohr radius, you involve the electron effective mass. For exciton, because it involves electron and hole, so involve the reduced mass. Let us calculate what is the binding energy and the Bohr radius for gallium arsenide. This is the permittivity in free space value. Gallium arsenide have a relative dielectric constant of 13. This electron and hole effective mass, and can calculate the reduced mass. So based on equation 2.7.12, okay, the binding energy is equals to the reduced mass, okay, over M0 times the Rydberg energy over epsilon R squared. So you plug in all the value, you can find the binding energy of the acetone of the gallium arsenide is about 4.7 MeV. The Bohr radius, again, is based on this equation. So basically is M0 times the relative dielectric constant times the Bohr radius of the hydrogen atoms over the reduced mass. That gives you about 117 Armstrong. Now, the total energy of the exciton is basically, in the whole system, it will be the band gap plus the energy of the relative motion plus the center of mass motion. The relative motion we already calculated, okay, will be the epsilon b times 1 over n squared, and then the kinetic energy is h bar squared k squared over 2m. The k c is the wave vector, okay, of the electron plus the hole. In this case, okay, since we have two particles, which is the electron and hole, okay, when we plot the Venn diagram, this is the energy as a function of k. This k is not represented as the electron wave vector. It's the wave vector of the electron plus the hole. So this is the ground state of the crystal and not the top of the valence band. But the minimum energy, again, is the band gap energy. Okay. Now, if we take Kc equals 0, then Ke equals to minus Kh. So we are saying the magnitude of the wave vector of the electron is equals to the magnitude of the hole. And that happened in most cases for the semiconductors. So we'll drop this term. So the exciton energy will be Eg minus this term. And when n equals to 1, it will become the binding energy. So the exciton energy is Eg minus the binding energy. Or sometimes we call this the free exciton transition energy. So based on these two particle picture, EB over 1 n squared. So n itself range from 1, 2, 3 as an integer quantum number all the way to infinity. So when n equals to 1, we measure to the continuum. This will be the binding energy of the exciton. And then this is the band gap energy. So the band gap energy minus the binding energy, that give you the exciton energy. So Eg minus epsilon b. So that give you the free exciton transition energy. Next session, we will discuss more on the bound exciton. Apart from the free exciton due to the free electron in the conduction band and free hole in the valence band, that give you the free exciton due to Coulomb attraction. There's also a possibility the electron can attract, impurity can attract exciton, and that gives rise to a bound exciton, which we will discuss in the next session.